time, I'd like to inform all parties that today's call will be recorded. If you have any objections, you may disconnect at this time. Again, today's call will be recorded. If you have any objections, you may disconnect at this time. Thank you, and we will begin momentarily.
Hello and welcome. This is Karen Fox with NASA's Office of Communications, and I appreciate everybody joining us for this media telecon about James Webb Space Telescope, what's been happening the last couple of weeks, and what is coming up next. We will have just a few opening remarks, nice and quick, and then we will switch to questions from media on the line. As a reminder, you can dial *1 to get into the queue for asking questions. Here on the line, we have Keith Parrish. He is the Webb Observatory Commissioning Manager at NASA Goddard Space Flight Center in Greenbelt, Maryland. We have Lee Feinberg, who is the Webb Optical Telescope Element Manager at NASA Goddard. Amy Lowe is on the line. She is the Webb Vehicle Engineering Lead at Northrop Grumman in Redondo Beach, California. And we have Jane Rigby, who is the Webb Operations Project Scientist also at NASA Goddard. So with no further ado, I will toss it over to Keith first for his introductory remarks.
Yeah, good day, everybody. We're just really excited to announce today that Webb is officially on station at its L2 orbit. And we've just been, this is just capping off just a remarkable 30 days. So our team this morning or this afternoon fired what we call our station keeping thruster. They did that, they fired that thruster for about 10 minutes. Actually 5 minutes, let me correct that, about 5 minutes. And we put about 1.5 meters per second in. And that pretty much capped off all of our mid-course correction maneuvers that we've been doing along the way. So a super duper shout out to our flight dynamics team that navigated us all the way from Earth orbit all the way out to L2. Our Delta V team and our propulsion team all have just did a remarkable job to get us to this point today. So since the last time, a couple weeks ago, we've also been very busy doing a lot of other really good stuff since we finished our deployments. We actually we actually did all of the mirror deployments, got them off of their launch, out of their launch configuration, and Lee will talk a little bit more about that. The spacecraft team has continued to put the spacecraft through all of its paces. The flight operations team and the mission operations team and all of our engineering team have really become comfortable with operating Webb and really continuing to get it, getting to know it. Over the past few days, we've actually got our Ka band, or what we call our high-speed data system or our communication equipment up and running, and we can transmit at the high data rates that we need to get all of that awesome science data back down to the ground when we start doing science. The last 30 days have been absolutely remarkable, and we've got it behind us. And, it's an incredible accomplishment by the entire team. They continue to put in long hours and just incredible achievement by so many. And, the last 30 days, we call that 29 days on the edge or 30 days on the edge. And we're just so proud to be through that. But on the other hand, we were just setting the table. We were just getting on station, getting this beautiful spacecraft from unfolded and ready to do science. So the best is yet to come, and I'll turn it over to, I think, Lee, to talk a little bit about the telescope.
Okay, thanks, Keith. So after we deployed the mirrors, each mirror moved forward by about 12.5 millimeters. We did position them in their best position to start optical alignment, so we used other degrees of freedom in the hexapod systems. Now all 132 actuators are working completely nominally, and they're working at these very cold temperatures. The coldest mirror is actually the secondary mirror, which is now about 35 Kelvin, which is roughly minus 400 degrees Fahrenheit. So those actuators are about that temperature. In terms of looking forward, the telescope alignment is going to take about 3 months, and it'll start once NIRCam is cold enough in about a week. We expect that the telescope alignment will start by looking at a bright isolated star, and we'll get 18 separate images that'll be very blurry because these individual telescopes won't be aligned. So we'll align them, and then we will put those 18 images on top of each other. We call that stacking. And then we start the most important part of telescope alignment, which is aligning the primary mirror in a way that we call phasing. And that actually puts the primary mirror, all those 18 segments, it aligns them to act as a single monolithic mirror. They're actually aligned to about 1/5000th of a human hair. And the final phase of alignment will be to align the secondary mirror and the primary mirror together in such a way that the telescope is aligned for all 4 science instruments. And that's the last thing we do, and that'll happen during the final phase of the telescope alignment. Should I turn it over to Amy Lowe at Northrop Grumman?
Hello, folks. This is Amy Lowe, and as far as the spacecraft and space vehicle goes, over the next few days, we'll be finishing up a series of our planned calibrations and really dialing in all of our subsystems to where they need to be. What we've been doing over the past month or so has been trending a lot of our telemetry, and as Bill had mentioned previously, getting to know JWST better and better. We're working both at the Mission Operations Center and also here at Redondo Beach, where I am. The spacecraft remains healthy. Like Keith mentioned, one of the highlights has been turning on our high-gain antenna so that we could get high data rates back. That's been something I was really looking forward to, and it's been great to see it in operation. Moving forward, basically over the course of the next week or so, we are getting ready for the real reason why JWST is on there, which is really to support the science instruments, starting with the turn-on and the telescope alignment like Lee mentioned. So we're pretty excited that the spacecraft portion has been going as well as it has, and looking forward to the science instruments. And I think that lets me turn it over to Jane.
All right, hi there, I'm Jane Rigby. I'm the scientist on this panel. So everything we're doing is about getting the observatory ready to do transformative science. That's why we're here. And so over the 6-month commissioning period, the next 3 months, as Lee said, are all about getting the mirrors aligned, so they're working as one unified telescope. And then the last 2 months of commissioning will make sure that the science instruments are working and that they are ready to do science. So I'm happy to take questions about that aspect of the process. Also happy to talk about the fantastic science that we're planning for the first year that is why we are doing Webb. Webb will be doing more than 300 observing programs in the first year. Most of those fall into 4 broad science themes about the first generation of galaxies that formed after the Big Bang, how galaxies evolve over the history of the universe, how stars and their planets form, and then all about planetary systems, both our sun's planets and planets that are orbiting other stars. And so 2 of those key science topics that are really great to highlight, we're going to be studying the atmospheres of planets that are orbiting other stars to understand what their atmospheres are made of. In addition, some of those planets might potentially be habitable, and we'll be looking for evidence of habitability. We'll also be studying through these very deep studies of dark parts of the sky, the first generation of galaxies that formed more than 13.5 billion years ago. So we're seeing that light only a couple 100 million years after the Big Bang, when it left those galaxies and started a long journey over most of the history of the universe to get to us. So we're a month in, and the baby hasn't even opened its eyes yet, but that's the science that we're looking forward to.
Thank you so much to everybody. We will toss it now to the operator, who will open up the lines for questions. And I will remind everybody in the room with me, as well as Amy, when we answer questions, because we are only audio, please do identify yourself every time so everybody knows who you are. And with that, I'll hand it to the operator.
At this time, if you'd like to ask a question, please press *1 and record your first and last name. Again, that is *1, and please record your first name. Our first question comes from Jeff Foss. Your line is now open. You may ask your question.
Thank you. Jeff Foss of Space News. I wanted to ask about the timing of the maneuver, why the orbit insertion maneuver took place at 2 p.m. on Monday. What was the timing that led up to that particular point, particularly when in some of the pre-launch planning we talked about doing the maneuver at L plus 29 days, and today is L plus 30 days. Thanks.
Yeah, hi, this is Keith Parrish. I'll answer that. So a good thing about how we've been managing our fuel and the maneuvers that we did for MCC-1A and 1B back on December 25th and December 27th. Wow, long time ago. Anyway, because of that, we had quite a bit of flexibility about when we did this maneuver. So we chose to do it on Monday at 2 p.m. and that was for logistical reasons for our team. Also for our ground resources around the world, we just took advantage of everything to do it today because it just made a lot more sense for our team to do it today, and it cost us no penalty. So we did move it one day from the 29, as you mentioned, but again, no penalty on fuel, and it was logistically and technically a better day to do it.
Okay, our next question comes from Bill Harwood. Your line is now open. You may ask your question.
Thank you. It's Bill Harwood, CBS News. A question for Lee Feinberg. I know the segments, the primary mirror segments get positioned one at a time, one actuator at a time. Is there any way to tell us how fast that moves? And fast is probably the wrong word here, but I'm curious about how quickly they can move in rough and fine mode, and how long it might take to get a single segment properly positioned if you didn't have to go back and tweak it. How long that process takes for a given segment. Thanks.
Well, let's see. The big moves we've already done. Those were sort of the slowest moves. So when we were deploying essentially a millimeter at a time, all 18 mirrors, and all 18 primary mirror segments and the secondary mirror. So all of those actuators together, I mean, that was roughly 8 hours-ish time to do all that, to move a millimeter. So that gives you some idea of how fast things can move. But in the future, we don't expect to be making moves that are that large. And in fact, the farther we go in the process, the smaller the moves. And so, by the time we get farther along, they should be pretty quick, the moves. A lot of the time it's just getting set up, with the right timing on the spacecraft and getting data down, getting data processed. So a lot of the time actually will be spent doing that, not actually moving the mirrors and the motors.
Thanks.
Our next question comes from Elizabeth Howe. Your line is now open. You may ask your question.
Hello, thanks everybody. And this one is for Keith, I think. Is there any chance that you could give some insight as to how these maneuvers went compared to past missions that were using Lagrange points? Maybe if there were any lessons learned you might have taken from these past missions that help with Webb? Thanks so much.
Yeah, so, going to L2 is we're not the first, but it's not something you do every day. So every mission is very, very unique. NASA flew a mission called WMAP quite a while ago that actually used the moon to help with a gravitational assist to get to L2. So every mission is really, really unique. So it's kind of hard to have a big database of learning from those, other than the fact that it's been proven that it can be done. Like I said, our flight dynamics team and our navigation team is quite plugged in to the community of orbit mechanics around the world. So they all knew how you would do this. So really we didn't, other than Ariane, the Ariane spas had launched a mission back a few years ago. That was sort of a little bit of pathfinder for them, launching something to L2. So obviously we took from them how well they could do it, and they actually were able to do it a little bit better because of their experience launching the L2. So yeah, no real lessons learned. What it does take is a lot of detailed planning, and again, everything was executed flawlessly mainly by our flight dynamics team as they planned out our route to get to L2, and then our spacecraft team fired the rockets at the right time.
And as a reminder, if you'd like to ask a question, please press star 1. Our next question comes from Marina Corinne. Your line is now open.
Hi, everyone. A question for Keith, I think. Now that the L2 burn is behind you, can you give us an updated estimate on how long Webb's science operations might last now, given its fuel supply? What's your most specific estimate now?
Yeah, so we've had that question before, and I think, our big burn was back on December 25th. In contrast, that was over a 60-minute burn, compared to today's 5-minute burn. So as you can see, most of the reporting that we did out prior on our longevity of fuel applies and wasn't affected at all by today's maneuver, other than we used very, very tiny amount of fuel. So yes, we're very, very happy with our estimated lifetime and of fuel. It's going to extensively exceed our 10 years, and whenever we do fine tune a number, which we are going to do, we plan to do that over commissioning. Once we fine tune that number, everybody's going to be really thrilled by it once we do. So it's just a degree of how thrilled, but ultimately we'll keep fine tuning it over as we get through commissioning.
Next question comes from David Curley. Your line is now open.
Thank you very much. From Discovery Channel. A couple of questions. In lay terms, can you tell us about A3 and A6 mirrors, the fact that you launched with the problem, how that went? Were you nervous? Did it go exactly as you planned? And secondly, can you explain L2? Is it kind of like a an eddy in a body of water? I'm just trying to help explain to our audience where you are. Thank you.
So this is Lee Feinberg. I'll take the first part of the question. We kind of knew that one was coming. So a little bit of the history of A3 and A6. I know a lot of people were interested in that. After we put the mirrors onto the telescope, this was when we were integrating the telescope at Goddard, we did notice that two of the position sensors, these are called LVDTs, it was two of the A-side position sensors and one B-side position sensor were not operating the way we expected. But what we figured out was that these position sensors actually are a differential measurement, which means you're subtracting two things, and one side of them was working fine. And so we realized that if we did a special temperature calibration, we could still use that position sensor. And so that's why those mirrors kind of worked in a different way. We had to, when we used those position sensors, we had to know the temperature, and we had to put that into sort of our operational sequence. That's all that was. We were very confident it would work. We'd actually had done this before. We weren't particularly worried about it. It was just a different sequence of things. And really what this did is it allowed us, when we were in the integration and testing, it just saved a lot of time and effort to try and remove position sensors very late in the game. So this was a way to kind of just do things very efficiently from the building of the observatory.
You can turn L2 over to...
Yeah, you want to take the L2, Jane?
Yeah, okay. Or Amy.
So you asked for the layman's view of L2, and I will tell you that the way I see it in my head is like a Pringles potato chip. Okay? It isn't a valley. If it's a valley, everything would collect there, and then you'd have a lot of space junk, and that wouldn't be good. It is a saddle point, so it's the middle of the Pringles potato chip. So it is a semi-stable point in our solar system. It is helpful. You know, we never want to get over to the other side of the potato chip. Then we start drifting away from the Earth, and we don't want to do that. So if you think about staying on one half of the potato chip and just kind of inching up it and then letting it fall back down gently, and then inch your little stone back up and then let it fall back down, but never get over the top of the potato chip. That's what we're doing in L2. We're in orbit around L2 on the Earth side, so we don't drift away. And that's what we do. We're just going to keep pushing the rock up the potato chip and letting it fall down for the life of the mission.
I'm going to use that as a headline.
Oh, no. It's a good analogy.
Our next question comes from Leo Enright. Your line is now open. And Mr. Leo Enright, if you could please check your mute button.
Okay, are you hearing me now?
Yes.
Okay, I have a potato chip question.
Oh, no.
I'm just wondering what your margin of error was today. Yeah, the delta V was something like 1.5 meters per second, which is kind of, I guess, what I would do if I had to just run a little bit faster after my dog, if I was going for a walk. So I'm just wondering, what was your margin of error before you went over the top of the potato chip and ended up spinning off into space?
Yeah, and this is Keith Parrish, by the way. So exactly right. Our whole goal of getting out to the L2 point is to not exceed what we needed. So we inched our way there, and we started that inching with the launch of the Ariane. We actually told them to not make us too fast. Actually, put us a little lower than what would be ideal. And then we put in a little bit more velocity with our Christmas Day MCC-1A maneuver. Then we took a little bit of a look at that, and we put a little bit more velocity in with MCC-1B. So we did so well with those first two maneuvers. We just need a little bit more today, but we always underburn. So even though we were only putting in roughly 1.5 meters per second, as you described, is not a very much extra. It was still a little bit under. We'll get a report out, a full report out from our flight dynamics team later tonight or tomorrow on whether that was 1.4, 155, all the way out to a lot of decimal places. The bottom line here is that we did not overshoot, and we are in orbit around L2. So even if we had not done the 1.5 today, we still would have been in orbit around L2. We would have not overshot it. What would have happened is we like to tune the size and shape of our orbit by doing these really, really tiny maneuvers. And the best way to think about it is that we have station keeping maneuvers that we have to do, as Jane said, to keep us there at L2. So every 21 days, roughly, we're going to fire that station keeping thruster again, even smaller than we did today, to keep us on there. But we're always on the air. We're always going on the low side. So on the low side, our margin of error was very large because we really didn't even have to do the maneuver to get into L2. We really wanted to do today's maneuver to shape our orbit like we wanted it. And any more than that, any more than that, you could overshoot. But we've been planning on undershooting for since we launched. So hopefully that helps.
Our next question comes from Greg Redfern. Your line is now open.
Thank you, everybody. And I think this is for you, Lee, for our listeners at WTOP Radio. You mentioned that the telescope will be focused, the 18 mirror segments, using a bright star. Have you identified what star you will use? And if not, how will you go about determining which star you will use? And thank you very much, and way to go. Way to go today.
All right. Thank you, WTOP. This is Lee Feinberg. So, we actually have chosen the star. We need a bright, isolated star. And the idea is, the reason we want it isolated is we don't want to get confused when we have these 18 separate telescopes, and have too many stars, essentially. But the star is HD 84406. It's in Ursa Major. It's just near the bowl of the Big Dipper. And you can't quite see it with your naked eye, but I'm told you can see it with binoculars. So for those of you who want to go take a look at it, it was dependent on sort of, the period of time that we'd be, doing this. So, which star we use kind of changed, but this looks like the star we'll be using, since we expect to be getting going in sort of next week. So
it's a G5.
And it's a G5, as Jane just said.
Star.
So which means it's a lot like our sun.
Cool.
Next question comes from Marcia Dunn. Your line is now open.
Yes, hi, thank you. I know that Webb is sharing L2 with the two other operating spacecraft. I'm just wondering, any chance of a collision? I know it's a big space out there, but how do you keep them apart safely? And at the end of its working lifetime, would Webb be removed from that orbit so it doesn't, become a threat down the road, or how will that work? I'm just trying to get a handle on how many years now will Webb be at L2? Thanks.
Yeah, hi, this is Keith Parrish. Let's see. So L2 is a spot. However, we orbit L2 in a very large orbit, so it's not crowded. It's extremely less crowded than Earth orbit. So there's no risk of interacting with any other spacecraft. It takes about 180 days for us to do our loop or racetrack around our orbit at L2. I don't want to give exact numbers, but it's roughly 800,000 kilometers is the diameter of our orbit. So it's very large. And that's one thing we designed, like I said, our flight dynamics team designed that orbit to be very large around L2, and because it is, you can take advantage of all that room. So what happens at the end when we do run out of fuel? Yes, we do leave a little bit of fuel left over so that we can, passivate Webb if we need to, and what that'll do is it'll just put us into a solar orbit around the sun at that point. So there is that can be done if we're required to do that. But what we don't want to do is, L2 is unstable, as Jane mentioned earlier. So you do have to maintain that. So yes, we would at the end of its mission. Some future folks will make that decision and maneuver us safely into a solar orbit.
Thanks.
Next question comes from Joel Arkenbach. Your line is now open.
Yeah, thanks so much, and congrats on how the mission is going. Just to be clear about looking at this star, it sounded like you said that could start as soon as a week from now. One thing I'm wondering is, right now, is there light being gathered by the telescope? I mean, and do your instruments, are they turned on at all? I mean, do you have any data coming back showing that essentially, although it's not, the mirrors are not aligned, and you wouldn't have a clear image? I mean, is it fundamentally working? Can you address that?
Yeah, I mean, we have not started. This is Lee Feinberg. We have not started taking images yet. The instruments have to be cold enough. To start the telescope alignment, we need the NIRCam instrument in particular. And initially, we've had some heaters on to prevent ice from building up. Those have to be turned off in the next week, and then things have to get cold enough. The detectors and the optics have to be cold enough to actually get an image. So light is getting through the telescope, but it's not being recorded on a detector at this point. So that's really where we are at this point.
I apologize. Is this Keith or Lee talking?
That was Lee Feinberg talking.
Lee, you said light is getting through the telescope. How do you tell that?
Well, it's just, if you look at the design of the telescope, it's sort of an open architecture in a sense. And we know that the primary mirror is facing deep space, so we know starlight is hitting it. It's not well focused. We know that light's then hitting the secondary mirror, especially now that the mirrors are in their deployed state. They're pretty close to a real telescope in terms of their alignment. And then the next optic is the tertiary mirror, and it's open to the tertiary mirror, and it finds light's hitting the fine steering mirror. At that point, some of the light gets stopped in the instruments where there's some, there might be something to block the light. Some of the instruments, the light can get all the way through. So we just know based on the design that it's getting through there, but we don't have any detection yet. We won't have that, as I mentioned, until next week when we start the alignment and the instruments are cold enough.
Thank you.
As a reminder, if you'd like to ask a question, please press star 1. Our next question comes from Lisa Grossman. Your line is now open.
Hi, thanks so much for taking the time to do this. I was wondering how long it takes Webb to complete, so there's 2 orbits going, right? There's the Webb doing the up and down, the Pringle orbit, and then the Pringle orbits the sun. How long do each of those orbits take?
Yeah, so this is Keith again. So to go around our orbit at L2 or around L2 is about 6 months. Again, a very, very large halo orbit. As we're doing that, we're going around the sun, in a year with the Earth to keep that Earth-Sun always aligned with us. So yeah, it's basically we're going around the sun with the Earth, and then we're doing this large halo orbit. Again, it takes about 6 months to go around that racetrack or that orbit.
Thank you.
Next question comes from Hagen Warren. Your line is now open.
Hello, Hagen Warren with NASA Spaceflight. Thank you for taking my question, and a massive congratulations to the entire team. My question is, with Webb now at L2, how is the process of cooling the observatory going? How is the Cryo Cooler operating, and is the temperature where the team expected it to be by this point? Thank you.
So just to clarify, most of the cooling is happening passively because the telescope and the science instruments are in the shadow of the sun shield. So most of that cooling, as Lee said, that the secondary mirror is 35 Kelvin. That's really cold, right? 35 degrees above absolute zero, right? So all of that is happening passively. It's just hiding in the shadow, and it's really dark there. And we're rejecting all but 1 part in a million of all the sun's energy, right? So it's a kilowatt per square meter on the hot side, and it's a couple milliwatts on the cold side, right? SPF 1,000,000. So that's why things are cooling. It's just cooling because it's in the dark, cold shadow. There is a cryo cooler on board. Just to be clear, a cryo cooler means it's a closed cell refrigerator. It's not like previous missions like Spitzer or Herschel, which have cryogen on board that evaporates out the space. We're not doing that. We have a closed cell refrigerator, a cryo cooler. That's not on yet, right? So that doesn't happen until these instruments get cool. And this is a good point to say that as everything's cooling, we are spending a ton of time watching those science instruments and protecting parts of them that need to stay warm. as they cool. So there's a really careful process where we're tracking the temperatures of, oh my gosh, dozens of, in each science instrument, dozens of pieces in each science instrument, and controlling the temperatures as they cool. So everything's cooling down, and then we're keeping some parts warmer to make sure that ice doesn't get deposited in along the optical train. So the cryo cooler is a step that will come later. And that's, I should say, sorry, this was Jane Rigby. And the cryo cooler is just for MIRI. That's our mid-infrared instrument. That's the instrument that has to stay the coldest. So the operating temperatures for most of the instruments is about 40 degrees above absolute zero. MIRI gets chilled down with that cryo cooler down to 7 Kelvin, 7 degrees above absolute zero.
Our next question comes from Philip Pologorski. Your line is now open.
Hi, I'm Filip Pogorzelski from the Science Channel of the Polish Public Television. First of all, congratulations on all the JWST mission successes, and I wish you some more great discoveries. And my question, as the Lagrange L2 point is not fully completely stable, JWST needs some corrections in time to stay on the right orbit. How often and when they will be done? And the second question, how do you determine the precise position of JWST and in space? Is the measurement based on position of the stars, or maybe you have different methods? And thank you for the opportunity to ask a question.
Yeah, hi, it's Keith Parrish again. So we do maintain the L2 orbit, and again, the prediction is that every 3 weeks or 21 days, we'll do a small firing of the station-keeping engine or thruster that we use today. I should remind everybody that when we launched, James Webb was a completely different spacecraft. It was all folded up, so we had a thruster in a different location. Today was our first use of our station-keeping thruster because we're all unfolded and we're in an actual observatory. So yeah, every 21 days, we're going to use that station-keeping thruster. Again, it could be 18 days, it could be 25. We'll let our flight dynamics team figure all that out for us over the next few weeks. And then as far as position in space, again, our flight dynamics team does that via what we call Doppler tracking of our radio signals to the ground station and how fast our ground station antennas are tracking us. So they use a couple different tools, mainly the Doppler method on the radio waves to actually track our speed, our velocity, location, and speed in combination with some other methods. So that's how they tell where we are in space and what direction we're going, and they assess that data over long periods of time as they gather it on the ground. As far as where we're pointing, that's part of the science program and where to point and right ascension declination. That's all controlled by our ground system for pointing the telescope to whatever observation is of interest.
Hi there, this is Amy Lowe. Just to add that also on board we have a slew of instruments on the spacecraft like the star trackers and the fine sun sensors that lets us measure where the sun position is and where the stars are to know our attitude, i.e. where JWST mirrors are pointed in space.
Our next question comes from Irene Quotes. Your line is now open. You may ask your question.
Thank you, Irene Quotes with Aviation Week. Sorry if I missed this. Is the primary mirror also, the segments also now at the 35 Kelvin, or is that cooling still continuing? And is, for Lee, thanks for the detail on the HD 84406. Is that star intended to be used for the kind of entire 3-month alignment and stacking process, or is that just one target of possibly many that will be used during the time to align the segment? Thanks.
Yeah, so we pick a star that is in an area they call the continuous viewing zone. So we'll use it as long as we can, but we expect to hand off stars as we go here. So that's sort of the plan. As far as the temperature, the primary mirror is actually warmer, by design. Actually, the secondary mirror is the coldest mirror, so it will be the coldest mirror ultimately, and that's why it's the coldest right now. The telescope mirrors vary from roughly 60 degrees Kelvin to 80 degrees Kelvin, which I don't know in Fahrenheit, but it's probably like minus 350 degrees-ish Fahrenheit, roughly. Yeah.
In the minus 60, minus 50.
Yeah. And there will be, the mirrors won't all be the same temperature even on the primary mirror. There's actually, different temperatures as you go up the primary mirror. And we're seeing some of that distribution right now. The wing mirrors tend to be a little colder right now. They have a little bit more view of deep space. The mirrors in the center are attached to a lot of mass, and so they take a little bit more time to cool down. But everything is cooling down really well. So we're really happy, and thank you to the SunShield team who did obviously a great job, because for the mirrors to be this cold already, they're right where they should be. So we're feeling really good about where we're going to be. And in fact, the secondary mirror is already in its operating temperature range, and the primary mirrors are just hitting that operating temperature range. That's really critical, because that's the temperature at which we know the mirrors will perform the way we expect. So we're right on the verge of that now.
Thanks. And is the NIRCam target temperature the 35K?
No, well, it depends on which temperature you're talking about, but the temperature we need to start the wavefront process, the telescope alignment process, we need the optics and the detectors more along the lines of about 100 Kelvin, but ultimately the detectors will cool more in the lines of like 50 to 60 Kelvin.
Okay, so the point you're waiting for next week is to get to 100K, and then you can start with the...
Exactly. Yeah, once NIRCam is cold enough, both in its optics and detectors have to be cold enough so that they can actually form an image, and the optics have to get cold enough because they're actually designed to work at these very cold temperatures. They don't work as well at warm temperatures. That's kind of true of the mirrors, but it's also true of the optics inside of NIRCam. So we need everything to kind of be at these cold temperatures.
Thanks very much.
Our next question comes from Isam Ahmed. Your line is now open.
Yeah, thanks for taking my question, and congratulations to the whole team. This one, I guess, for Keith, just to push further, I think you said the remaining fuel should allow for more than 10 years, and we'd be announcing a figure soon, and it would be, people would be thrilled. Would you be able to give us any idea of how much longer than 10 years that might look like? And then again, for Keith or possibly Amy Lowe, I mean, hypothetically speaking, could a future mission, either crewed or robotic, refuel the telescope, to sort of take a big jerry can up there or replace some component which could, add to its life, hypothetically speaking? Thank you.
Yeah. Hey, this is Keith. Yeah. So when it comes to fuel, we are incredibly... We have plenty of fuel. We probably should take that off the table. We're going to extensively exceed our 10-year life, and you've heard numbers around 20 years. We think that's probably a good ballpark, but we're trying to refine that. So we don't think fuel is it's really going to be off of our mind as far as a life limiting thing going forward, regardless of what the final number is. Like I said before, it's going to, we're all going to be thrilled. I think the astronomical community is thrilled. The folks who built and designed Webb and everybody's just thrilled by that final number. So it's going to be, like I said, you've heard some of the numbers out there, and they'll be right around there when we fine tune it. As far as refueling Webb, again, we don't anticipate a need to do that. Again, we don't know what condition Webb will be in general when it does run out of fuel. That's a long way down the road, and we never want to limit our imagination. So I say never, but right now we don't anticipate a need to do that. Again, not quite understanding what condition Webb will be and say that 2 decades from now. But people are creative, and as you know, right now things are going. The advances in spaceflight are really going well. So who knows? Who knows what some future folks may want to do with Webb and visit it and do something. But right now, there's absolutely no need to think about fuel or refueling.
Thanks.
Our next question comes from Steve Gorman. Your line is now open.
Yeah, hi. Thanks very much. I have so many questions. I guess the one thing I wanted to ask about is the cooling down process. So again, just to make sure I understand, so you're waiting till next week because that's the point at which you expect that by then I think it's called the mirror cam. This cam, one of the forms which are going to be necessary to use to help align the primary mirror will be cold enough down to about 100 Kelvin for it to operate properly in order to do the alignment process with the mirrors, right? That's what you're waiting for. And
yeah. So this is. Go ahead.
Okay, and then Mike, I guess so. I just want to make sure I understood that correctly. And then the other thing was when you just to explain to readers, we keep talking about waiting for the various parts of this observatory to cool down sufficiently to whatever temperature they need to operate optimally. What is just? I believe I know the answer to this, but are we waiting basically for the telescope as a whole to cool down, waiting for basically residual heat that's mainly from solar exposure to dissipate in the shadow of the sun shield, right? It's cooling down from what? In other words, it's cooling down.
Yeah.
From
Okay. So
heat.
Yeah, so let me help you out a little bit. Let me start with the NearCam instrument. So a really key point is that, and this is a very unique thing about Webb. There's no other. Ground telescopes don't do things this way. But we're using the main one of the science instruments, the near-infrared camera, as our wavefront sensor. And we've actually inserted special little optical elements inside of the filter wheel, little lenses and other things that are going to help us align the telescope. But that near-infrared camera does have to be cold enough just to be able to, first of all, its detectors don't work at warm temperatures, so they have to be cold enough that they can take images. And we need the optics to work well. So yeah, that's what we're waiting for. As we go along the wavefront sensing control process, the alignment process, we will also be using the guider to stabilize things. And that happens about 10 days later. The guider actually has to get even colder, closer to 65 Kelvin. So those are the big drivers there. In terms of the cooling, well, so it was discussed earlier that the whole system is passively cooled. The reason we put up this large sun shield, these 5 layers of sun shield, is so that the telescope over time will cool down. You could think of it as, it's what we call black body emission, but basically we're trying to get the heat out of the system. The telescope started at a warm temperature, right, when we launched it, and it just takes a long time. You're emitting heat out towards deep space, which is extremely cold, and it just takes a long time to do that. So that's partially what we're waiting for. The mirrors have to get cold enough, number one, so that they don't generate infrared light, which would contaminate our images. That's why they have to be, our mirrors, like for example, in the primary mirror, they're designed to work between 30 and 55 Kelvin, and that assures that not only do we won't affect the near-infrared instrument, but we'll also not affect the mid-infrared instrument. So we have to get them cold enough. But they're attached to a structure behind them that is also very warm, and that structure has to cool down. And that's sort of what takes the most time, is that big, heavy mass that's holding it. It's actually a large composite structure, a bunch of harnesses, and all of that has to kind of slowly radiate heat to deep space. And not only that, for the tail end of our process, we have to get everything stable. So it's not just cooling it down to a low temperature, but it's getting it sufficiently stable, because that primary mirror with those 18 mirrors, those mirrors have to be stable relative to one another. That's not typical of any other telescope. Even ground telescopes don't do things this way. They actually have special little active things that keep the mirrors aligned. On our system, we have to get everything not only cold, but stable. So those two things kind of drive us. The cold drives us in the beginning to get images, and the stable drives us sort of midway through the alignment process so that we can converge on our solution. Hope that was helpful.
Yeah, thank you so much. But if I just say that the thing is cooling down, but it's basically just it's radiating off the residual heat of the overall structure. It takes time for that to dissipate into space.
Exactly.
Okay. Thank you.
Our next question comes from Paul Brinkman. Your line is now open. You may ask your question.
Hi, yeah, this is Paul with United Press International. Can you hear me?
Yeah. Yes.
Okay, great. I think this is for Keith or Jane regarding the commissioning timeline and first release images. I know you aren't going to tell us what those images will show, and sorry if I missed this at some point, but does anyone know when those images will be released? What does that timeline depend on? And specifically, will you be able to release images taken during commissioning, or does the public have to wait like the full 5 additional months to see something? Thanks.
This is Jane Rigby. The plan is to release the first beautiful images in a press conference about 6 months after launch. So that's about 5 months from now. So those are the early release observations, the EROs. So that is the set of data that show that the telescope is working, that the science instruments are working, and that this is indeed the transformative telescope that we expect it to be. I think you're also asking if there's additional data at that time. When we finish commissioning, we will release all the data from commissioning. So commissioning ends after that ERO press conference, and we'll open up the archive at that point, and so the commissioning data will be in there. So that means interested scientists from around the world can go take a look at that data. A lot of it won't be very interesting because it'll be those ugly, fuzzy pictures of stars out of focus that we had to laboriously drive into focus. But there will be some fields that will be of scientific interest, and we'll open up that archive at the end of commissioning.
And this is Karen Fox. Just quickly, a lot of this is still in conversation, and so as you've been hearing, there's a lot of different testing along the way. And if there is something that we can share before then, we certainly will. So the last question there was, what does it all depend on? And the answer is, it depends on everything, and we will definitely be sharing what we can when we can.
Our next question comes from Leah Crane. Your line is now open.
Hi, my questions have already been asked. I was just going to ask if we're going to be able to see commissioning images before that press conference.
So this is Karen Fox again, and the answer is absolutely. We'll share what we can, when we can, if we can. But it's certainly, as Jane was saying, there will be test images, lights, things that don't even look like stars. But if there's something that we can show, we certainly will.
Thank you.
But don't hold me to anything. We're figuring it out. That was the point I was making.
Next question comes from Daniel Ricardo. Your line is now open.
Hi, how you doing? Thank you. This is Daniel from Ardron, UI. We are a Spanish multimedia communication company. Thank you for your time. The first question, you had two little short questions. The first one is, when are you expecting for the first exoplanet observation? And the second one, short, based on the experience of building James Webb on more than 20 years, if you have new plans for make a new one but quicker. Thank you.
We'll all take it. All right, I think. This is Jane Rigby. I think I get both of those. Hola, hi there. The first question was about exoplanets. There are a series of programs, there are 13 of them, early release science programs, not to be confused with EROs, early release science programs that are designed to execute in the first 3 months of our normal science operations. And those include 2 different programs to study extrasolar planets. One of them is a direct imaging. We'll be looking at a planetary system by directly imaging it and blocking out the light of the star in a way that is a lot more complicated, but I always think of it as sticking your thumb over the star so you can see the planets. And then there's also a transit spectroscopy program in there, so studying a planet that goes in front of its star, and so you see the light of the star going through the atmosphere to you. Those ERS programs, early release science, are designed to be, we're going to front load them in our schedule, so we will observe them as much as possible in the first 3 months of normal science operations. The second half of your question was?
Future.
Oh, future missions. So certainly the Webb telescope, this method of deploying a telescope in space, of curling it up to fit inside the rocket and then unfurling it once it gets to space, that is something that we could do again. And in fact, the once every 10 years, the decadal survey of astronomy just came out, Astro 2020, and indeed recommended a large telescope in space. And the obvious way to do that is to deploy it in space. So yes, indeed, people are working on what the future would look like of future big telescopes in space.
Thank you. Thank you for your time. Really.
Our next question comes from Peasant Robbie. Your line is now open.
Hello. So I was just wondering, now that James Webb is getting ready to observe, I'm wondering if along its orbit, are there certain points in its orbit that are better suited for observing certain targets? Like halfway through the orbit, it's better suited to observe Enceladus, for example?
So our orbit, so the Webb orbit is basically, on the anti-sun direction from the Earth, right? So it's out there and it's in this little orbit around L2, going around twice a year. The main thing for scheduling, like when can we observe what, is that we have to keep the sun shield such that the sun and the moon and the Earth are blocked to the telescope, right? The telescope never gets sunlight on it again. That's the goal. Doesn't get Earth light on it either. So that means that that part of the sky down where the sun shield is, we can't look at at a given time. So at a given time, Webb can see about a third of the sky, it's 35%. And then that field of regard where we can legally point, that rotates slowly as the Earth and Webb go around the sun. And so any point in the sky is accessible over the course of a year to Webb. Webb can look at any given point in the sky during the course of a year, but at any one time, it can look at about a third of the sky. So this is part of what factors in as we make schedules. We take all of the targets that have been approved, and then we work out a schedule that minimizes the travel time between each target, like how far we have to turn the telescope, and that, of course, gets each target when it's observable. And there's a bunch of other factors too, like how dark the sky is for that piece of the sky, which changes with the year.
Hi, this is Karen Fox. We are coming up on the hour. We have 2 more questions from people who haven't been able to ask questions yet, and we will be taking those too, but then we will be wrapping it up. As always, if you have something you want to follow up on or extra questions that didn't get answered, you should feel free to send us an email, and we will try to get you additional information. But back to the operator for those last 2.
The next question comes from Jakai Goddard. Your line is now open.
Hi, Jackie Goddard from the Times of London. And congratulations, everyone. So we know that those big nail biter milestones are out of the way. But what if you now switch something on and it doesn't work? How much risk is now retired? To what extent is any potentially still ahead? Is there really anything that you could have got all of this way and then find that there could yet be a showstopper? Thank you.
Hi there, this is Amy Lowe. I'll just answer first for the spacecraft and sun shield portion. So in terms of all of the nuts and bolts on the observatory of things that operate, like on the spacecraft, everything has been switched on and checked out, so we don't expect anything not to operate. And I'll hand it over to the rest of the team for the telescope and instruments.
Yeah, I mean, in terms of the telescope, we still have yet to get optical images, so we still need to go through that and prove all of the optical systems work. As far as doing the actual alignment with the instruments, I mean, our plan is to do it with the near-infrared camera, which I mentioned earlier. That instrument has internal redundancy, so that's a good thing. And then we also have developed contingency plans to be able to operate even if there was an instrument that wasn't working. So there is a lot of robustness in our ability to do the alignment process. And then, of course, the instruments all have to come on, and they have some levels of internal redundancy, but they're all unique. So so each instrument kind of has to come on prove themselves in a sense. So that's kind of what's in front of us.
Thank you.
Our last question comes from Marcia Smith. Your line is now open. You may ask your question.
Thanks so much. I just had a couple of numbers that I was looking for. What was the exact duration of the burn today? You said it was about 5 minutes. Was it exactly 5 minutes? And is that about the duration of the burns every 21 days? And one last question, because I'm still trying to get my mind around the potato chip analogy. So is one orbit, is the center of the orbit at the bottom of the chip, and one orbit is up and tip and down, and then up and back down again? Is that one orbit?
Yes.
Yeah, hi, this is Keith. I'm going to throw that potato chip over to Jane since she caused all this confusion. But no, on the burn duration, yes, it was 5 minutes. We don't know. We have to download all the data from the spacecraft to get. Again, we are incredibly precise and accurate. So we're really talking about out to the millisecond when our thruster turned on and when our thruster turned off. So that's the kind of accuracy that we're looking for. But it was commanded to be 5 minutes. This actual station keeping burns that we'll do roughly every 21 days are going to be significantly less than that, on the order of a minute or even less sometimes. So yes, and again, I think it's important to get back to the fuel question. In fact, our use of fuel for getting to L2 is over, and we used, we didn't even use, nearly a third of our allocation to that. So all the fuel that we have left is for station keeping, which are small burns every 3 weeks, and then to dump momentum, which is built up in our reaction wheels as the solar pressure pushes us around a little bit. So that's the roughly 5 minutes, and we expect a full report from our flight dynamics team. Again, tomorrow after they assess the data, but we're really talking out into the milliseconds of differences between, 5 minutes and maybe 5.100 minutes. We don't know that yet. And for potato chip analogies, I'm going to go back to Jane.
That's my fault. Well, I can make this worse because I can put a donut on the potato chip, right? So yeah, if you've got an orbit going around the sloping down part of the potato chip, right? So you got a donut on your potato chip, right? Then that's that 180 days, twice a year orbit. But the point is, we just want to stay on our side of that, right? And that's why, as Keith was saying, we do these underburn, and we've creeped up to. That's why we've done 3 burns to creep up to the orbit that we want to be in, and now we're there.
So you are in a circular orbit.
Yes.
Yes, that's right. We're in a circular orbit around the second Lagrange point. We don't want to be exactly at the second Lagrange point. For one thing, then we'd be in the shadow of the Earth.
Kind
right?
of elliptical shape.
So yeah, it's an elliptical squashed thing.
Yeah.
But there's lots of orbits that are fine. We just need to be in a nice orbit around the second Lagrange point. That way we always have sun on the solar array.
Okay, thank you.
I'm not going to give you on gravitational wells and how the angle was meant to show where the forces are. This is Karen Fox again. Thank you so much for everybody being here today. And as I said, you should feel free to contact us if you didn't manage to get a question answered or if you have something that you need a follow-up on. Thank you so much to all of our speakers today, and looking forward to this whole journey with you over the next 5 months. We'll be continuing to update you as we go. As you know, nasa.gov/Webb, WEBB, is where we host things. You can get to our blog from there with mission milestones, as well as our Where's Webb and some of the other information we have up. Thank you so much. Goodbye.
Thank you for your participation. That concludes today's call. You may disconnect at this time. Speakers, please stand by.